Okay, guys. So far so good. Welcome to exercise 5 of the structural analysis with robo course. Okay. In this exercise 5, this is what we want to see. Okay, we have a beam here that is cantilevered at its beginning and has a series of hinges at D and B, and then roller supports at E and C, and basically it is loaded with point loads at different points. So this is what we want to model in this exercise, and the exercise says the compound beam is fixed at A, da, 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 da. There are hinges, da, da, da. So the question is to determine the reactions at the support, and this is the last beam exercise that we shall be seeing. Okay, from here on we will look at other types of structures. Okay, good. Let's go straight to robot to be able to model that. So we are here. We will take the 2D frame structures. Okay, so here we are. The very first thing we want to do, as usual, is to go and make sure that our units are set. Okay, we want to take the metric unit. Yes. Okay, and then we want to start drawing our beam. We'll use again a different approach here, okay? And this will be an introduction to something that you will see quite often when modeling your structures in Robo. So here we have our beam. So you have to agree with me. How many discontinuities do we have here? We have one, two. Okay, so we'll model this beam actually as one, two, three beams, right? Each of these beams, what separates them is a roller, or rather, we will have one, two, three, and 4, right? Because we need to put a point load here where, rather a node here where we will be able to model our support. Okay, so it will be first beam, second beam, third beam here, and then fourth beam this way. So to model this, we will not go via the grid method as we've seen so far, or just by mere coordinates. We want to introduce something known as structural axis, which is, as you can see here, the very first thing that Robo shows us in its frame of modeling. Okay, so you want to click there, and these axes are simply references that we give ourselves to be able to know exactly where our beams have the potential, or our structure have the potential to be drawn. There are some form of fictive lines, okay, that already represent where our structure will appear. Okay, in this case it is the beam. So these fictive lines will help us to draw the beam accurately. We want to draw lines that tell us exactly where the beam appears. Okay, so here it is presented in the Cartesian coordinate system. Okay, so we also have cylindrical for things like shell structures and things like that. But I digress. Right, let's focus on our Cartesian coordinate system. We are here on the x-axis. Okay, so the x-axis will define all the structures that have to be drawn in this direction, and as we can see, according to the x that we have here, and as we can see, our beam is purely on the x-axis. Okay, now the first beam will be drawn from 0 to 3. Okay, the second beam from the 3, right up to 6. So from the 3 to plus 3 again. So I'll have to show you guys this in different formats. Assume that we have is there something I can use here? Okay, let me take this. Assume that we have this is our, come on, it's no longer drawing. That has to draw a line. Oh my god, I think I over pressured my my pencil. So it's okay, let's continue now. My PDF. So assume that we have this as our Y, okay, and then, or rather in Robo it is Z, right? Yeah, it's okay, just make the connection. And here we have, excuse me here, I'm drawing with the mouse app, it's not very so, and then here we have our x. Okay, so what does it mean? It means that this point here would be at position 3 of x, right? This other point here would be at position 6 of x. This other point would be at position what, 7 of x. Okay, and the last point here would be at 7 plus 2, which would be at position 9 of x, right? Exactly. So these are the positions that we want to represent here. Okay, the points that would delimit the different lines. So what are we saying? We are on position here. Okay, we want position 0 first of all to add, because the first point is at position 0. Okay, right here, that's where A is found. So position 0 will add that, and then we have position 3 will add that, and then we have position 6 will add that, and then we have position 7 will add that, and here we have position, excuse me, we have position 9. We will go right ahead and add that, right? So that is our x. At the level of z, we have just one position, right? Our y, we have just one position. All of that happens at z equals to 0. Okay, the axis here is constant. If we assume that this is you know the x-axis is the y-axis equals to 0, right? That's mathematics. Good. So we are here, and what we want to do now is to apply. Okay, so once we apply this, look at what happens. These are fictive lines that show us exactly where our beam will appear. Okay, so now it's very easy for us to come right here and draw our bar from those lines. Okay, so the first will come from here to here. Okay, since it is continuous from this point, I can just click on drag here and it will automatically want to draw a line from the previous point that I just clicked on, and click here and then click here and then click here with no stress. Okay, so that's our beam. I hope that was very well understood. Okay, so the next thing that we want to do is apply our supports, right? I just want us to finish with supports and releases. So for the supports, we'll just click right here. Okay, so we have fixed support, right? That's correct. We have a fixed support here at the level of the first point, and then we have a roller support where and where a roller support, okay, at these two last points here. Okay, so we'll have to define that. It's not found here. So we'll just say roller Z to indicate that it blocks, it's a reaction that blocks the Z direction, the Z displacement. So I don't want UX, I don't want that, I just want the Z. Okay, so I'll add that and close. Good. So we can apply it at 4 and 5. Good. So the next thing we want to do is to model the releases. Okay, all these things we've seen them already. We've explained all of these things in the previous exercise, right? So we can just go right ahead. Previous exercises, sorry, and we can just go right ahead now and model, right? So the next thing is to apply the releases. So we'll come to geometry and releases. So we have here n releases. You remember what n released rotate are, right? So it means that to apply this, we have to come to where the arrows are pointing in that direction, okay, and then we can click, and it does that, and it has to always point the second node, right? You remember that. Okay, here too we have a release here. We also have one here from our good, and here. Perfect. So I think that's what we have. Good. So that's what we have. Okay, a hinge here, and oh, sorry about that, and a hinge there, right? And a hinge here. Good. The next thing we want to model is our supports. Okay. So for this one, we have no problem. It's applied at a particular node, right? So let's model that one first. 8 kilonewton. Yeah. So for that, we need to define a load type first. Okay. So let's just choose the dead load, close that, and then we can then accurately define our loads under that particular load type. Okay. We have node, point load. So these are the directions here. Our load is pointing how in the Z direction, right? But opposite to that, to the global orientation. So we'll have here -8. That's all. We have no moments, okay, and we have no inclination of the force around around the y-axis. So I can add that and just come and apply it right here. Good. The next load is, let's look at that, is 6, right? And it's applied how? At 2 meters away from the beginning of the bar. Because remember, from D to B is a different beam, okay? And the 6 is applied at 2 meters away from the beginning of the beam. So to do that, we'll choose the bar because this point load is not applied on a node. It is applied somewhere within the bar, okay? So this is what we'll select here, the bar force, right? And still, it is following the Z axis, so we'll have -6. So here we'll choose absolute and say 2 meters. All of these concepts were already explained in the previous exercises. Good. So we'll say 2 meters and it's global, right? No problem. We'll just add that. Now we'll choose in such a way that it goes from, yes. So the arrows again matter. So when I click there, that is my 6. Okay. So what is left to be applied? What is left to be applied is the 12 kilonewton, and it is at 1 meters or at half of this beam. Okay. So it is still a bar force. It is still this one, but we can take relative, right, and say 0.5 in the middle. And what's the value of the force? 12 kilonewton. So here we'll have 12 kilonewton, and we can add that and come right here. Yes, it doesn't matter whether it's like that or like that, right? And click, and we have a force there in the middle. So let's be sure of what we've done. Okay, so we have that, right? Clean and clear. So that's our system. All we need to do now, what do we need to do is just to run the calculation and check the reactions, right? So we'll go right ahead and calculate. Okay. So wait for the calculations to be over. Okay, so we have this instability noted. We said we'll explain all of that in later videos, right? Because it's not the first time we are having this one. So we'll explain that. We just go ahead with our calculation. And now we want to check the results. What are the results? Okay, let's display the reactions. Okay. Mm, we want to see, yeah, we want to see the reactions, everything, because we have a fixed support here, okay, and plus that description. So let's apply that. So that's what we have. Let's check it with what the document gives. So these are our answers right here. Okay, so let's go ahead and check that with what the document has. That's the exercise 2.27. So we can go right here. 227. Okay. Okay, so we'll just zoom there. Come on, come on, come on, come on. Okay, so 227, we have 12, 4, 10, 30. That doesn't look like what we have, right? Here we have 12. Let's go node by node. Let's go step by step. So 227 NE 12 kilonewton, NC 4 kilonewton. Let's look at that. So we're supposed to have, here is 4 is accurate, here is 12 is accurate. But our answers are not exactly the same, right? Because we have what? We have this extra 6.4, rather 0.64, 0.64, which are not supposed to be there. And the reason is because we calculated this beam considering the self weight of the beam that was given to us by the cross section. So to correct that, we have to come to load here, okay, and go to load table. So I just want to take advantage of this to show a particular concept, okay. Right. Before I do this, let me just show you something. Before I do this, are you seeing this green here? This indicates that the results that you have now for reactions are actual, okay? They are correct for the structure that you are having, okay? So now let's go and remove that load table, okay? And this is the self weight here. We don't want this self weight to be there, okay? So we'll just press that and press Control X and say it even tells us the perform operation will cause the changes in database containing that. So the result status to not available. Okay. Do you want to continue? It's a way of saying that your results after removing that load will no longer be accurate. It means you will need to redo the calculation. So you see the yellow here, okay, or the orange signifies that your results are out of date. They are not up to date. So for you to bring them up to date, you need to recalculate, okay, with the new loading that we've left here. Yes, no problem. Continue with that. Good. So now what do we have? Mm, so we have NE to be 12 kilonewton, NC to be 4 kilonewton. Let's check that. This is our NE here, normally 12 kilonewton. This is our NC, which is 4 kilonewton. And then what is left? We have AY to be 10 kilonewton and MA to be 30 kilonewton. So that's what we have here. AY 10 kilonewton and this negative 10. It means their own was measured clockwise. That's why it's positive, right? Their moment was measured clockwise. So that is that with this exercise. Okay, so from next exercise onwards, we'll be seeing different kinds of structures. We'll see a truss, how to calculate the reactions of a truss, how to model a truss, calculate its reactions, how to model a frame and calculate its reactions. So see you in the upcoming exercises.